ॐ भूर्भुवस्वः तत्सवितुर्वरेण्यं भर्गो देवस्य धीमहि धियो यो नः प्रचोदयात्.
Okay, today in this session we'll talk about scheduling algorithms. But before we start the scheduling algorithms, let us summarize what we had covered in the previous session. We saw that there are different types of the evolution of operating system and how the functionality has been added as the time rolls on. And we have also seen the process concept, what is process, and what are the different states of a process, and what do you mean by preemptive multiprogramming and non-preemptive multiprogramming. So now this process is a representative of an operating system, and it's a very important logical resource. Now it has to be scheduled on CPU in order to execute itself. So scheduling algorithm is actually an algorithm which is used for in which way this process has to be allocated to the CPU. Now generally this scheduling decision will be invoked in the following cases. As we have seen in the previous session, that when a process is created newly, okay, it will be in ready to run state. Then from ready to run state, the scheduler will take decision, any one of this process which is there in ready queue to be given to the CPU. And when it is given to the CPU, then the state of the process we call it as running. Then possible events may occur. Either the process run to its completion and we call it as terminate state, or process may go for some IO. Okay. And this is called IO wait, because of some IO event. Then if that event elapses, again the process will be shifted back to ready to run state. Now the scheduling algorithm, when it gets invoked, as I have told you, that scheduling is nothing but taking a decision. This decision as to which process to be allocated to CPU is taken at different point of time, at different scenarios, at different steps. Okay, when a newly created process comes to the ready to run queue, a newly created process enter into the ready to run queue, then scheduling decision will be taken place. And in second situation, suppose a process is running on CPU and it has run to its completion. It means when a process terminates, then also scheduling algorithm will be invoked. And now there is a possibility that a process performing some IO event, okay, goes to IO wait. So from running to IO wait state, then also scheduling algorithm gets invoked. And from IO wait to ready to run as well. Now there is one more situation wherein, assume that, as I have told you in the preemptive multiprogramming, wherein every process will be given a time quantum, and that process will be running, the time quantum is the maximum time which can be given to any CPU for its execution. Okay. If the process takes longer time, then it has to preempt, go back to the ready to run queue, and again it will be given chance for scheduling onto this. So this is called timeout. So when timeout happens, it means when generally this transition is possible, this from running to ready to run. Now these are the 5 different situations wherein scheduling algorithm will be invoked. Now in non-preemptive scheduling algorithms, actually the scheduling algorithms can be preemptive or they can be non-preemptive, and they can be non-preemptive. What do you mean by preemptive? Means what do you mean by non-preemptive? Non-preemptive means the process will leave the CPU only under 2 situations: when a process terminates, or when a process moved from running to wait. In these 2 situations only, the process will leave the CPU. So these are the 2 transitions which are possible, and the scheduling decision will be invoked if any one of these 2 cases happens. Okay, only in non-preemptive scheduling algorithms. Non-preemptive scheduling algorithms, and remaining this 1, 4, 5 are actually preemptive scheduling algorithm. Yes, okay, which help us in knowing how to evaluate a given algorithm, whether it's working good or not. Now the main idea or the central theme about the scheduling algorithm is the resources of the computer should be utilized very efficiently and effectively, and we know that the very important resource is CPU, and this CPU has to be utilized up to 90 to 100%. Okay, the throughput should be more. So how this scheduling algorithms will be calculated, this how they will be evaluated, against what parameters? Okay, there are few scheduling criterias. If the algorithm performs well in the following scheduling criterias, then we take decision that this is a good algorithm. But in real time, generally there is no one specific algorithm which is suitable for all kind of processes. It depends upon the type of processes, which we'll see now. So there are different scheduling criterias. The first time is we evaluate a scheduling algorithm on throughput. CPU utilization. What do you mean by throughput? Throughput is nothing but the number of processes that can be completed in a given unit of time. If a system is completing 5 processes in a given unit of time t, and another system is completing 10 processes in a given unit of time, here time is same. So the throughput, which system will be having higher throughput? This system will be having higher throughput, because it could able to run or execute more number of processes in a given unit of time when compared to this CPU. So this is possible by smartly taking decision which process has to be executed at what point of time. So this all depends upon the decision what we take depending upon the type of CPU processes. There is nothing but throughput. What do you mean by CPU utilization? CPU utilization is generally on an average CPU can be utilized for up to 40%, but it is possible to take its utilization up to 90 and 100%. So how to increase this CPU utilization? CPU utilization can be increased by taking smart decisions as to which process will be allocated, so that IO and processing should run parallelly. There is nothing but CPU utilization. So whenever you have a process and you want to schedule this process onto the CPU, now there are many things which are associated with this process. Suppose if this process is taking longer time for execution, of course throughput comes down. Okay. And yes, CPU utilization goes to higher, but here throughput goes down because the number of processes you are executing are less, because this process is taking much time. So there are few parameters, or there are few criteria which are under scheduling criteria which are associated with the processes. Those are nothing but waiting time of a process. Suppose a process is ready to run. If a process is ready to run but CPU is not available, in that situation what this process has to do, of course it has to wait for till it get its turn. If a process is in ready to run, it doesn't mean that it will be scheduled on CPU. Okay, it depends on scheduling algorithm, which type of process the scheduling algorithm is favoring and when it turn comes. Okay. So the amount of time which is spent by a process in a ready to run queue is called waiting time. So waiting time is defined as it is the amount of time spent by the processes in ready to run queue. Might be this waiting time can be continuously or when first it has been brought to the ready to run queue, and how much time it is spent in the ready to run queue is called its waiting time. And there is another time called turnaround time. Okay, then you have completion time. Okay, you have service time. We call it as also as burst time, and we have okay. Now let's talk about response time also. Okay, what do you mean by turnaround time? Now these times can be explained very easily with the help of this diagram. Now assume that this is a timeline and it starts from 0. Now it is possible that a process is started at time, okay, when it has been brought into ready to run queue, its time starts. Now suppose when process P1 has been submitted to the system here, where it has been given chance after 5 units of time, then the amount of time it has spent in ready to run queue is nothing but your waiting time. Now turnaround time, it happens probably like this. Suppose if process P1 is executing, afterwards the scheduling algorithm has taken decision to schedule another process. Okay, now this another process is given, suppose a little more 10 units of time, and then again assume that process P1 has been scheduled. When process P1 is scheduled, again it is running for more 5 units of time. Now here what happened is the individual amount of times, okay, at different point of time in ready to run queue, the process is waiting for its turn to get its complete. So the total amount of time, including waiting time, response time, okay, all these times are called turnaround time. So the total amount of time taken by the process for its execution, okay, is called turnaround time. Now what do you mean by service time? Service time is nothing but, or burst time is nothing but the actual amount of time a process takes for its completion, to execute to its completion. Suppose a process takes 4 units of time, but because of scheduling decision, okay, it may wait for 2 units of time in queue, and again when it is scheduled onto the CPU, it will be executed for 4 units of time. So total time here is 2 units plus 4 units, which is 6 units of time. So burst time here is only 4 units, but waiting time is 2 units, okay, and turnaround time is 6 units. Now completion time is the process has started at unit at first unit of time, it has been completed at 20th unit of time. So the process, when it has completed its execution, meaning it is moved from running to terminated state, is called completion time. Now what do you mean by response time? Response time is very important to understand, and it plays very prominent role in time sharing systems. Now generally user doesn't tolerate much of the processing time, response time. Whenever a user gives input, okay, and the system gives output, response time doesn't means how much time a user has to wait for getting a response, okay, for getting output, but response time is nothing but it is the time interval between the user has submitted the request and response has started from the system. It doesn't mean that output has been given, but the response has been started from the system. So this time interval between the user has submitted the input to the system and started getting a response, okay, this time interval is called response time. More the response time, then it's good in time sharing system and better utilization of computer resources. And if you don't have a proper response time, then generally there is bad response time we have in batch processing systems, right? But we have a good response time in time sharing systems, where CPU time is shared between them. Now when we have understood once all of these processes, now we'll take a scenario, we'll create a scenario wherein multiple processes, and we have a uniprocessor system, and multiple processes want to run onto the CPU, and we have a scheduling algorithm. Now that algorithm will take decision how this processes has to be allocated in order to get full greater throughput. Throughput should be more, and CPU utilization should be more, and response time should be less. And because less the response time, user enjoys a lot, right? And completion time should be less, and turnaround time should be less, and waiting time should be less. Okay, no process, nobody wants a lot of waiting time when it has submitted any request. They expect the output to be fastly. They don't want much of the waiting time. But however, we cannot decrease the burst time, because burst time is actual time which is taken by the CPU, taken by the process to execute to its completion. So at any circumstances, this burst time cannot be reduced. It is constant. So the total time, the turnaround time, okay, in best case it can be burst time will be equivalent to turnaround time, where waiting time will be 0, and in worst case turnaround time will be far better than burst time. Okay. So let us talk about what are the different scheduling algorithms. And how they operate on different processes. Let's take an example. Suppose as I have told you that process can be identified in a system by a unique ID called process ID. Assume that when there are 3 processes which are there in our system, a system has 3 processes and their associated burst time, and we take an algorithm called first come first serve, FCFS algorithm. First come first serve algorithm. The name itself reveals a lot of secrets. The process which has been submitted to the ready queue first will be given chance first. Burst time is the amount of time which is associated with those processes. Suppose I have 3 processes, P1, P2 and P3, and they are taking this time 24, 7 and 3. Okay. These are the burst times associated. What is the meaning of this table? Here each and every process is uniquely identified by this process ID. For process P1 to run to its completion, minimum amount of time it takes is 24 units of time, and process P2 takes 7 units of time, process P3 takes 3 units of time. Now, in what way I have to, now assume that all of them have been submitted to the system, at the same point of time. So time is 0. All of them have submitted together. Meaning, so there is one more time called arrival time. So arrival time is nothing but it is a time when the process has been submitted to ready to run queue. When it has been entered into ready to run queue, its timer starts. So that is called arrival time of that process. So the arrival time for this process, let's assume it's 0, 0, 0. But actually in real time they may be same or they might be different, right? So now we'll see the working of this FCFS. How does it work? Generally this FCFS works in non-preemptive mode. It works in, the mode of this algorithm is non-preemptive. Meaning it doesn't leave CPU, the process when once it is scheduled onto the CPU, it doesn't leave CPU unless and until it has completed its execution or it is performing some IO operation. Right. So we'll draw a Gantt chart. Now always Gantt chart starts from 0. It doesn't necessarily means always process arrival time starts from 0. Arrival time starting can be anything, but the Gantt chart starting time should be 0. Now in first come first serve, let us assume that I am accepting the processes in the order in which I have written. So there are many possibilities because all of the processes are to run queue simultaneously, and I am taking, I'm free to take any one of these processes. So suppose if I have taken process P1, when process P1 is taken, we know that the burst time of this process P1 is 24 units of time. So this process, actually this Gantt chart is nothing but, it is the CPU utilization chart. It means it gives us areas in which the CPU is busy and the area in which CPU is not busy. So when I write 0 to 24 here, it means the process P1 has taken CPU time for executing process P1. So now when process P1 has completed its execution, then only it leaves CPU. Now CPU will become free from 24 units of time. Then process P2, then I am taking process P2. When process P2 is taken, we know that process P2 is taking 7 units of time. So the total amount of time which is needed for this process P2 to execute is, this 24, which is waiting time of this process, plus this 7 time is burst time. So which is equivalent to 31, right? 31. Then process P3 has been given chance, and process P3 run to its completion in 3 units of time. So the waiting time for this process is 31 plus 3, which is the burst time. So always, you cannot have any time which is less than burst time, right? So waiting time, turnaround time will always be equal to or greater than this burst time. Okay, so it is 34. So this is the Gantt chart. So your CPU is busy from 0 to 34 units of time in order to execute all of this process. If we add all of them, are we getting the same 34? 24 plus 7. Yeah, 10, 34. Yes, 34. Now, let us find out the different times which are associated with this process. First time is waiting time. So let us find out what is the waiting time for process P1. So here I'll draw and chart. Here I'll have process P1. Now for process P1, I will write what is the waiting time and what is the turnaround time and what is the completion time and what is the response time. Let's find out all of these times for a given process. Process P1, okay. It has come at time 0 and it has been responded at time 0. So waiting time for this process is 0. And turnaround time of this process means the total amount of time taken by this process to run to its completion is 24 units of time. Now this is the best case because here burst time, okay, we'll write here burst time also. We know actually it's there already, burst time. So when burst time and turnaround time is same, this is the best case. Now completion time of process P1 is 24 again, and response time is response time is also 0 because the time interval between the user has submitted the request and it has started getting response is 0. As and when it has submitted, it has got output. It is getting the output, not got the output, it's getting the output. So these are the different associated times. Then now let us see process P2. Now process P2, actually it has been submitted to the system at time interval arrival time 0, but it has been scheduled on CPU at after 24 units of time. Why it has not been given here? Because process P1 was already executing. So process interleaving is possible in uniprocessor system. Process overlapping is possible in multiprocessor system. We are dealing with the scheduling algorithms which is based on uniprocessor model, right? So now up to 0 to 24, the process waits. Okay, process P2 waits. Then it has been given chance. So waiting time for this process is 24, and turnaround time is nothing but waiting time plus burst time. So what is the waiting time? 24 plus burst time. Burst time is also 24. What's the burst time for process P2? The burst time for process P2 is 7. So it is 7. And completion time for process P2 is 31. Okay. And what is the response time? Now how do you find out the response time? Response time is nothing but when the process has been given to CPU. Okay, it has been given to CPU at 24 minus waiting. It has been given to the CPU at time 0, but when it has started responding at time 24, right? So we will find out the response time by subtracting 24, which is from when the response has been started, minus when it has arrived. So 24 minus 0 is 24 again. And the next process P3. Now process P3, what is the waiting time for process P3? Process P3 has actually submitted to the system at time 0, but it has been given chance at time 31 units of time. So waiting time is 31. And turnaround time for this process is, it is the total amount of time which has been taken by this process to complete its execution. So it is 0 plus turnaround time is 0 plus 24 plus, so total amount of time is nothing but the waiting time, which is 24 plus 7, which is 31 is the waiting time for this process, and completion time is 34. Okay, and response time is 31 minus 0, arrival time, which is again 31, and of course we know the burst time is 3. So these are the associated times of each and every process. Now let us find out what is the average waiting time. So average waiting time, always we want in a system average waiting time to be reduced, average response time should be reduced, and there should be maximum CPU utilization and maximum throughput, and turnaround time should be reduced, waiting time, average turnaround time, average waiting time, and average response time has to be reduced. Okay, this is our goal in scheduling algorithms, right? So now here we will find out the average waiting time. The average waiting time is nothing but sigma of all this, add all of them. Okay, 0 plus 24 plus 31, 0 plus 24 plus 31 by total number of processes are 3. So it gives me 55 by 3, okay, which is equivalent to 3, 4, 5, 2, 3, 6, 3, 7 are 21, 3, 8 are 24, okay, then 0.1, so 18.3 units of time. So average waiting time is 18.3, okay, and let us find out the average turnaround time. Average turnaround time is 24 plus this 24 plus, what is the turnaround time for process P2? For process P2 the turnaround time is 24 plus 7, yes. And what is the turnaround time for process P3 is 31 plus 3. So yeah, 31 plus, it should be 3 is 34. So average turnaround time is 34 plus 31 plus 34 by 3. So average turnaround time is 24 plus 34 plus 31, 9, 6, 7, 8, 9 by 3. So 3 1s are 3, 3 2 are 6. So let's take it as up to 90, for example, then 30 units of time approximately. Okay. This is the average turnaround time, and this is the average waiting time. Now this, if here we are following first come first serve basis. According to this algorithm, if we allocate a process P1 to a processor, then it doesn't leave the CPU unless and until it has completed its execution. But we have a lot of drawbacks here. There is actually a lot of possibility here to reduce the average waiting time and average turnaround time. How? Just by making a smart decision among the available number of processes, Now here actually it's an unfair. Suppose now this is CPU intensive process, okay, it is taking lot of bus time, lot of CPU time in order to execute itself, and they are taking considerably less, relatively less time, okay. So now let's assume that they are IO bound processes and they are CPU bound processes. Now here the algorithm is not making any fair decision. It is giving much of the time to this IO bound processes, whereby unnecessarily all this process, even though their bus time is 7 and 3, their total turnaround time is surprisingly 31 and 34. 31 and 34, right? Okay. So this is the turnaround time of this process. So now this is not good. Why? Because here what is happened is, this is called the situation is like this. Suppose if a process who is IO intensive, okay, it needs lot of CPU time to complete its execution. When it has been given to CPU, now there are many processes which want IO activity. They are IO intensive, but they need very little amount of time to execute on CPU. Okay, when they are waiting in ready to run queue for their turn to come, but because there is IO bound process which is running, okay, they are waiting unnecessarily. While they are waiting, actually we have two resources here. One is